let's actually dive into the last concept we're going to talk about today. So I think maybe in the first lecture of this course, Stephen made a joke about how he thinks everything is game solving. The same thing is true for me at this point. Somehow I just see games everywhere I look. But today we're going to be talking about a slightly different game. It's going to be kind of important and interesting for different reasons in the sort of inverse RL kind of imitation games we talked about earlier. I think it's one of the more interesting things I've worked on in the last few years. Before I get too much into this, though, who's scribing for today? Okay. All right, let's get into it. So today we're going to talk primarily about two questions. The first is going to be when is the Bradley-Terry assumption inaccurate? Like when is this sort of strong parametric assumption we made that basically the probability of some completion to a prompt being referred to another completion to a prompt basically being proportional to the sigmoid of the reward difference. When is that true? When is that false? And perhaps more importantly, when this assumption is violated, as I'm going to argue frequently happens in practice, what actually happens to the downstream RLHF procedure as a result, right? I think oftentimes in theory, you would make assumptions and they're violated, but you always have to consider what the actual implication of this assumption being violated is and what that means for your downstream algorithm. So that's maybe the first question I'm going to try and talk about. And then I'm going to give you a sort of an alternative way to think about RLHF that doesn't require this sort of strong parametric assumption on the way preferences are generated. And this is going to lead to a nice objective, let's say, but something that's like rather hard to actually optimize. And I'm going to kind of conclude the lecture by talking about how we can actually efficiently optimize this thing. I'm just going to kind of be using a bunch of different things we've learned over the span of this course. So let's get into it. So what I'm going to argue right now is basically the Bradley-Terry assumption is going to be violated when our word function can't explain either individual or, I think more often, aggregate preferences across a population. And this essentially leads to some sort of downstream mode collapse behavior in the RLHF algorithm you've kind of put together. So let's make that a bit more explicit. So I want to introduce a concept called a preference matrix. So kind of thus far when we've been talking about things in this class, right? We basically said that, okay, you get some data set D of preferences, people liking some things, liking other things less. So here again, the sort of squiggly greater than means I prefer Psi1 to Psi2. This sort of just squiggle means I'm kind of equally preferable. So let's think about how we can actually represent this sort of thing as a matrix. So I'm going to say that our preference matrix P here, basically each cell in this matrix is going to correspond to the probability in our data set that some trajectory Psi1 is referred to some other trajectory Psi2. So let's fill in the obvious parts. There's going to be a Psi1 here, a Psi2 here, a Psi3 here, same thing here. Okay, so we have a matrix. People often think about the diagonal of a matrix first. Can anyone tell me what kind of must go on the diagonal here? So that corresponds to how often I prefer Psi1 to itself. 0.5, right? Because if I give you, two options that are equally good, right? It's basically a coin flip between them, right? Like if I tell you, okay, do you want this apple or this identical apple, right? So the diagonal of this matrix will always be 0.5. I think this is sort of just a reasonable assumption to make in general, right? Like people don't prefer things to themselves, right? Okay, now let's try and fill in the rest of this matrix, right? So, okay, so we got data in our data set that said, Psi1 is referred to Psi2. I guess all the time, we basically always see this. So what does this cell have to be then? Anyone? So that sort of cell right there is the probability of Psi1 being referred to Psi2. And if my data set always says that Psi1 is referred to Psi2, what is that probability?
1.
1. Good. Okay. This is going to be 1 here. I guess the same thing here is true for Psi1 and Psi3, right? So I'm going to fill in a 1 here. And then, if I say basically in my data set I see Psi2 referred to Psi3 as often as I see Psi3 referred to Psi2, right? And the probability of preferring one to the other is 0.5. Okay. So I've sort of filled in the stuff above the diagonal. Now, here's a question. Do I know what these three cells are? Why or not? Yes, why?
Just 1 minus the corresponding entry.
Right. And why must that be true?
Because probabilities have to sum to 1.
Exactly, right? Essentially, the probability of preferring psi1 to psi2, right? And the complement of that event, preferring psi2 to psi1, those two events kind of split the space of things that can happen completely, so the sum of them must be 1. So basically, anything above the diagonal, you do 1 minus that, and that gives you the sort of flipped element over the diagonal. So I'm just going to fill this in for you guys. So this is going to be 0, is 0, it's going to be 0.5. Right? So we have this matrix. So let's just maybe emphasize that diagonal of this matrix is always going to be 0.5. And across the matrix, you're basically going to do like a 1 minus x kind of thing to flip it over. Okay, cool, interesting. We can take our preference data set and represent it as this matrix. So here's a question. Did I make any sort of meaningful assumptions when I went from this preference matrix, so far from this preference data set D to this preference matrix P? Think about the construction we just went through. Were there any sort of assumptions I made that were not basically just basic facts about probability? No, right. The probability of, these two is just like an axiom of probability that an event and a complement have to sum to 1. And something being preferred to itself is, I think, is like, kind of crazy, right? No one would prefer an element to itself. So I can basically go from an arbitrary preference data set P to a preference matrix representation P without making any actual meaningful assumptions on it. So I'm going to say that this translation from D to P is basically without loss of generality. I'm really making no meaningful assumptions on the way people behave when making this. Okay. So now let's try and think about a reward function. Right. So I don't want to actually go through trying to do logistic regression in my head here, so I'm going to be a little bit more hand-wavy in this lecture than I usually am. But, okay, if I have, psi1 being preferred to psi2, right? This probably means that any reward function that rationalizes this behavior needs to give a higher reward for psi1 than for psi2. Same thing must be true for psi1 and psi3. And I guess because it prefers these two equally, probably wants to give them the same, right? They're equally good options. R psi2 equals R psi3. Okay. Can anyone tell me a reward function that satisfies these properties? There's a bunch of them. Pick whatever one you want. So I've essentially given you constraints on the values. And I'm just asking for the actual values for these three numbers. Yeah. Sorry, did someone raise their hand?
Yeah. I was just going to say the simplest one would just be the one that returns the corresponding entry from the matrix.
Yeah, definitely. So, I guess, what do you mean by that, right? Because my reward function here just depends on a single together, right? The matrix depends on.
Oh yeah, it depends on two. Yeah. I guess you could do the average across, if you average the rows.
Yeah, that would be an option. Or basically, if I just tell you that I want these three things, right? Anything that basically sets R1 higher than R2 and R3 and sets R2 and R3 to be the same thing, that's kind of a valid thing to do, right? So we'll get back to the sum thing in a bit. But let's say I pick something like, I don't know, R equals 1, 0, 0, something like this, right? So when we go from D to P here, I basically said we're making no assumptions. When we go from P to R here, the kind of rest of this lecture is going to be arguing that essentially we're making a relatively strong assumption, and that this is a thing that actually frequently is violated in practice and kind of makes a lot of this sort of stuff we talked about earlier maybe not achieve the optimal performance you would like. So maybe to give you a bit of intuition for why this might be true, let's say something like the following happened, right? Let's say I prefer psi 1 to psi 2, and I prefer psi 2 to psi 3, and I flip this around, and I prefer psi 3 to psi 1, right? Then I basically need to have a reward function that ranks psi 1 over psi 2 over psi 3, and psi 3 over psi 1, which I can't do, right? Because those sort of constraints conflict in some sense, right? And this maybe gets at the point I think Ryan was getting at, where really what I have here is a matrix that depends on both the column and the row. And I'm trying to collapse it into a scalar value. So I'm basically trying to compress this matrix into a vector. And you have to have assumptions if you're doing that compression in some sense. And the underlying assumption is basically that there is an ordering over all these things that people agree on. So exactly why you might have these sort of cyclic or intransitive preferences is like a deep question. I'm not going to talk too much about that. But at the highest level, I think it usually boils down to one of two reasons. One is basically that maybe people compare different options on different features, right? So let's say, you know, psi 1 here is like a green apple, and psi 2 here is like a red apple, and psi 3 here is an orange, right? Like maybe I compare apples based on color, but you know, I don't have a preference between colors between apples and oranges. I just like, maybe I like oranges more or less. And when you compare along different sort of criteria, you try to collapse it all into one unidimensional preference, this can lead to this sort of appearance of intransitivity. The other reason, which is what I'm going to spend most of the rest of the lecture talking about, because I think it's probably the thing that happens more commonly in practice, is that maybe individually you, I have rational preferences. We can order all completions to a prompt. But when we sort of aggregate group preferences together, this can lead to the appearance of intransitivity, even if no individual person is being irrational or intransitive or things like this. When I say irrational, what I mean is that if you have intransitive preferences, I can essentially like Dutch book you, which means that I can keep trading you back to what you had before and like make money on every trade, right? Because there's sort of a cycle of preferences. So that's what sort of irrationality means here. And we've heard of things like utility theory or the von Neumann-Morgenstern axioms. That's a more formal way of saying what I just said. Don't worry if you haven't though. Okay, so we have this sort of preference thing here. Now I want to maybe walk you through why I think this sort of intransitivity actually shows up in practice. So let's say I give you a slightly less dense data set, right? So we can fill in the elements like we did before, so 0.5 along the diagonal, psi 1, psi 2, psi 3 here, 2, psi 3 here. And okay, so I've told you psi 1 is referred to psi 2. So I can stick a 1 here, and I can stick a 0 here. But if I don't give you any other information, right? Unless you basically assume that everything you saw was worse than what you saw in the preference data set, or worse than what you saw in the worse or better than what you saw in the preference data set, I can't really fill in these two cells, right? Which means I can't fill in these two cells. So I think what often happens in practice is you don't actually get a single person or a single group of people with similar preferences to tell you what they care about everything, right? You only get some sort of partial coverage. You sort of end up with these matrices where you think about trying to represent then data set in this form, you basically have these sort of blank squares where you don't really know what's going on. So the challenge happened is when you have a bunch of these sort of partially completed matrices and you kind of squish them together into one matrix when you aggregate people's preferences, right? Which happens when you're doing data collection at scale and you're asking a bunch of different raters, hey, what you like compared to this thing or that thing. So I'm going to make this a little bit more visual now, but let's say we have three groups of people. Group 1 really prefers, or really all the data you see is they really like rocks compared to scissors. Group 2 really prefers paper compared to rock, and group 3 really prefers scissors compared to paper. And you can think about maybe they have a preference over the third thing that's rational and we just don't see it or something like this. So we get these kind of three groups of preferences. Now let's think about, okay, if I wanted to take these three groups of preferences and use them and represent them in this sort of matrix representation. So hopefully everyone can kind of believe me that you see matrices that look like this, right? So I'm going to see 0.5s along the diagonal, right? That's always true. I'm going to basically fill in the one square that I know here, and then I can basically fill in the thing across the diagonal like this, and then everything else is sort of left unfilled, right? So now what I'm going to do is think about aggregating these preferences, right? So let's say there's basically 1/3 of the population looks like this, 1/3 of the population looks like this, 1/3 of the population looks like that. Then preference aggregation basically corresponds to averaging these matrices, right? And if there's like a question mark, there's something that's unfilled, I'm basically going to use the other value that's there. And you'll notice if you look at this carefully, I essentially never have in any of these like kind of cells off diagonal, I never have any like conflicts in the sense that like there's either a question mark or a 1, and I never see something. There's like never two things that aren't a question mark. So I'm sort of just like I don't have to actually average anything here. I'm just adding. So when you kind of squish these matrices together, you'll see something that looks like this, where I have the 0.5s of the diagonal, and I copied in the 0 or the 1s I saw before, right? So you see a matrix that looks like this. So let's think about this for a second. So one thing that maybe is sort of obvious, right, is that each of the rows here have an equal sum, right? So row 1 here has a sum of 1.5, row 2 here has a sum of 1.5, and row 3 here has a sum of 1.5, right? The other thing that is sort of interesting here is there is no like reward function I can write down that rationalizes these preferences, right? Because I would simultaneously need to have a reward function that sets the reward for rock higher than that of scissors, paper higher than that of rock, scissors higher than that of paper. Right. So I need to basically set this R greater than this R, this R greater than this R, and this R greater than this R. Does that make sense? Does everyone kind of buy what I'm saying here? Good. So now, for this particular problem, you might look at this and say, okay, it seems like given all three of these rows, the sums are the same. It doesn't really matter what I do, right? Like I could just kind of give you rock, paper, scissors equally likely, and who really cares, right? But I want to maybe give you a slightly more complicated example of this phenomenon, where I think you'll start to see what I think happens in practice. So I'm going to give you another matrix that kind of has intransitive preferences. Basically what I did was I shuffled things a little bit. And let's say my reference policy here is going to be uniform. It's going to be 1/3, 1/3, 1/3. And let us say I'm going to put I'll just give you the sum for each of the rows here. It's going to look something like, 1.2 here, I guess 1.8 here, and 1.5 here. So if you think about essentially the reward model as basically trying to say, okay, how often compared to something generated from the reference policy was an option preferred? We can really think of the reward function we get out as being having the same kind of ordering over things as the sort of row sums, right? Because I'm saying I'm going to pick a rock and I'm going to pick uniformly across these three for my comparator. So can anybody tell me an example of a reward function that, let's say, kind of satisfies this ordering? You can even You can give me a particularly simple one if you like. I'm trying to make a point here that like even though there is no reward function that actually explains the underlying round trip preferences here, I can still try to actually fit one. So can anyone give me an example of a reward function that basically follows this ordering of things?
Any numbers that are the same order?
Yeah, great idea, Stephen. Thanks. So maybe I'm just going to use the exact numbers I had here. So 1.2, 1.8, 1.5, kind of like Ryan suggested earlier. So the exact values of what you get here depend on the particular like logistic loss or whatever loss you use to fit your reward model. But basically, you should see a reward model where you set a relatively high value for 1.8, the thing in the middle, the paper, and a relatively smaller value for the other two. And let's maybe try and put this together. So my pi hat RLHF, right, is going to look like my, it's probably proportional to my reference policy, which is going to be pi ref, times basically the exp of 1 over beta times the reward model, where beta is basically the strength of the KL regularizer. And because pi ref is kind of uniform, this is not going to affect this, right? So roughly speaking, even if I have a relatively small increase in the reward score I set here compared to the other two, when I pass it to this exponential, the optimal policy is going to put a huge amount of probability mass on it, right? Essentially, like beta is often something like, let's say, 0.05. So basically, what this operation is saying is multiply the thing you got over here by 20 and stick it to an exponential. So you're going to end up with way more probability mass concentrated on this one mode here. So you're going to get this thing that looks like a really small amount of probability mass here and a huge amount on the main. So this is what I mean by mode collapse, in the sense that there's no reward model that actually fits the data. When we try to pick one, we're sort of in this like misspecified setting in terms of reward models, right? When we talked about imitation, we talked primarily about being misspecified in terms of policies. Now we're talking about it being sort of misspecified in terms of rewards. And the sort of downstream implication of this fact is that when you pass to the exponential, you're going to put a huge amount of probability mass on this thing here. You're going to see this sort of collapse of generation diversity to just the preferences of even a slight majority of the population. So I'll pause for questions in a moment, but maybe to sort of connect things a little bit further. You might say that, okay, this is like an example with 3 options, right? This is really just rock, paper, scissors, right? I want to make the point that this problem only gets worse as you have a larger set of options, right? Because as I get more and more options, it's more and more likely I'll see these sort of intransitive preferences. There isn't some single word function that explains the entire population of raters' preferences across every completion to a prompt, right? Like if that doesn't kind of strike you as true, think about the contrapositive, right? Like for this to not be true, what I would need to happen is that every single rater in their minds has like pre-agreed that there's a single word function that tells them for every possible natural language completion to a prompt, we agree on what is better than something else, right? That's an extremely strong assumption. And if you actually look at any of these sort of preference data sets, you'll see that people can barely agree on like whether 2 completions are preferred to another. There's no sort of total ordering that exists in the sort of aggregate preferences. And I guess my point here is that like this becomes less and less likely as you get an even larger set of things. Right? Like maybe people can agree on 2 or 3 things in order. That if I tell you literally order every single possible natural language string, like across everyone, even in this class, right? You're not going to all agree on what that should be. So that is maybe the problem. And in maybe the last 20 minutes or so, what I'm going to try and talk about is the solution, or what I think a natural solution is. I don't think there's only one answer here. I think this is a sort of nuanced and deep question, but there's one answer I'm particularly fond of, and that's what I'm going to talk to you about today. And it's going to relate to this idea from social choice theory called a minimax winner. And the core reason we're going to like this option is it's essentially not going to impose the assumption of transitivity of preferences or that there is a single shared underlying reward function that explains everyone's preferences. And then we're going to talk a little bit about a kind of fun algorithm to actually compute this minimax. So let's think about our right? I'm going to do a kind of perhaps seemingly innocuous transformation here. So what I'm going to do is I'm going to take this matrix, I'm going to multiply it by 2. Oh, yeah, please go ahead.
I had a question about the previous. So, like, what should a good reward model distribution look like in your opinion? Because it seemed like, to me, like the exaggerated mode, which is in this case probably the mode collapse, was it a desirable property because it at least gave us confidence about the confidence of the RM in a single preference as opposed to it's like producing a uniform distribution or a random distribution of all preferences possible. So, like, I agree it should not be a uniform distribution. I agree it should not be a unimodal distribution, but is it supposed to be a bimodal or like what's the?
It's a good question, right? So I think you're sort of hitting the nail on the head in the sense that, like, right, we don't want to be unimodal. We don't want it to basically tell you a uniform distribution over things. And the question is, how do I essentially pick in the entire space of things? And essentially what I'm going to give you is an argument for why I think a particular game theoretic objective gives us a natural way to figure out what we want to actually do. But I think that, like, this is sort of like a choice in a sense. A sort of fundamental property of a lot of results in social choice theory is, right, you can't always get what you want. There's things like impossibility theorems that basically say that you can't make everyone happy all of the time. So you have to figure out, essentially, if you're going to compromise, what is the way you're going to compromise? And I'm going to talk about a particular version of that. That is a good question. Okay. Any other questions, actually, before I go on? Okay. So what I'm going to do for this matrix is I'm going to multiply it by 2, and then subtract off 1. So, okay, so if I take 0.5, multiply it by 2, I subtract 1, I guess I get 0, right? So I'm going to matrix that has zeros all along the diagonal. That's interesting. And let me think about what happens when I do it for these other elements, right? So I guess 0.7 is going to map to 0.4. 0 is going to map to -1. 1, I guess, is going to stay at 1, right? Okay. And let's think about the things on the flip of this, right? So 0.4, or let's say, think about 0.3. So let's say I multiply 0.3 by 2, and I subtract 1. I'm going to get -0.4, right? If I do the same thing for 1, I multiply 2 and subtract 1, I'm going to still get 1. And if I do it for 0, I'm going to get -1. So notice there's something sort of interesting here, right? Where I have a matrix where the diagonal is all 0. And basically, if I flip you over the diagonal, you get the negative value now, right? So people will often call this sort of matrix anti-symmetric. Like a symmetric matrix would mean that when I flip you over the diagonal, you get the same value, right? But here I'm getting the negative of that value. Again, I'm not making any assumptions here. I just have constructed this matrix, right? So, for the interesting leap, perhaps. What is this matrix? Like, what can I? Well, we've talked about these sorts of matrices a lot in this class. What is this matrix? Exactly, right? It's a payoff matrix. For what kind of game? Anyone? Yes, it is a zero-sum game, a minimax game. Good. Well, there's one other thing that's special, right? The payoff matrix is anti-symmetric. What does that tell me about the game?
That your gain is the other person's loss.
Put differently, that if you and I were playing this game and we swapped strategies, I would get the same reward you did. So beyond, your game is, their loss being your game is just a property of all zero-sum games, right? But more nuanced than that here is that we have a symmetric zero-sum game. So it's not always true that if you swap strategies with your opponent in a zero-sum game, you would do as well as they did. But here, because the game is symmetric, that must be true. So kind of without making any assumptions, right? I basically constructed a symmetric two-player zero-sum game. So now that we have a game, we can think about solving it, right? So I'm going to define a concept. So this goes by a bunch of different names in the social choice theory literature. It's been invented a bunch of different times. I think the earliest citation I found was 1965. These days, computer science people will call this a von Neumann winner or a minimax winner. And if you ask like a social choice theory person, they might call this a maximal lottery or something like this. But we basically said that, okay, maybe a thing we can do is, given we've written down this game, is try to compute the Nash equilibria of it, right? So we're going to say, give me a pair of policies, pi 1 and pi 2, such that when I sample two actors from psi 1 and psi 2, I'm trying to basically solve this two-player zero-sum game. And let's think about the kind of maybe the equilibrium strategy here for a second for the first player, right? Because I'm doing this whole kind of game theoretic thing, right? I'm essentially asking you to be robust against an arbitrary, or maybe, let's say the worst case comparator, right? So basically what I'm saying here is, okay, I want you to pick me a policy pi 1 star, such that if I compare you to an arbitrary policy pi 2, you can't do that poorly. And this is interesting, right? It's sort of more robust in a sense that we're not really just looking at what we saw in the training data. We're saying no matter what I compare you to, I want you to be robust too. And the thing here that's kind of interesting, perhaps, is that let's say I computed this pi 1 star, right? Am I making any assumptions when I compute this pi 1 star? Like for this pi 1 star to exist, right? So,
Like for minimax theorem to hold?
right, so we have to so we have to have the standard assumption for the minimax theorem to hold, right? We need like the Sion's conditions, right? But this is a matrix game, so that should hold. And we also kind of made no assumptions when we're actually constructing this kind of thing inside the basis, right? Actually constructing the payoff here. So the thing that's kind of cool here is this von Neumann or this minimax winner basically must always exist. Versus the sort of argument I gave you earlier saying that, okay, if I can't even fit a good reward model in the first place, a decent RLHF policy might just not exist, right? It might just lead to sort of mode collapse behavior. So I am not going to go through this in great detail because of the time limit. But the sort of cool thing you can prove about this is that I'm basically going to be preferred to any other policy with probability at least 1/2. If this isn't clear, think about how for this game here, right, let's call it, I'm just going to use let's say 2p minus 1. I think about any probability vector pi transpose pi, so the value of the game for any symmetric set of things, right? This must be 0, right? Because I'm going to compare you to yourself. You can't be preferred to yourself. And then if you think about how this is 0, I add 1 to that, I divide by 2, I get 0.5, right? So when I add 1 to this, plus 1 and divide by 2, I get 0.5, which roughly speaking means I'm going to prefer to any other policy with probability 1/2, right? Maybe a little bit more explicitly, you can think about getting this by basically thinking about, let's say we do it for the min player, so over pi 1, pi 1 transpose 2p minus 1, pi 2 star, right? This must be upper bounded by that, which is the definition of a Nash equilibrium, right? going to back out this, you must win with least probability 1/2, or not lose, with probability more than 1/2. And kind of to reemphasize here, we don't require any assumptions on this underlying shared R. So maybe the sort of takeaway from this idea really is that we can pick a policy that is robust against this worst case comparator. We can guarantee that it will be referred to any other policy we could pick, probably at least 1/2. And I don't need to make any assumptions on all my raters having a shared underlying reward function in their head, which even if it were true, might not happen because of this sort of like reference aggregation kind of complexity of things. So I don't want to try and solve a linear programming problem in class, so I did this ahead of time. The minimax winner for this particular game looks like this: 5/12s, 5/12s, 1/6. I think the thing that's kind of interesting here, right, is like, okay, so we do put a good amount of probability mass on this center row, right? That is sort of the thing that has the highest row sum. Kind of reasonable, right? But what's interesting, right, is this row has like a sum, right, of 1.5. This row has a sum of 1.2. And we put more probability mass on this one compared to that one, right? And the reason this is sort of interesting, right, is that this is giving us something qualitatively differently than what we would have gotten if we just fit a reward model, right? In a sense, we're trying to be more robust. We're saying, okay, I'm not going to make this assumption of an underlying reward model. And I want to say, okay, I just want to say that if you compare me to any other policy, I do kind of well in comparison. And that's why if I kind of, let's say, play, you can kind of work this out more carefully on your own, but basically if I play paper often enough, this means that, relatively speaking, I should be playing rock more than scissors. Because a policy that could try to exploit me if I play paper too much. So we talked a lot about how kind of one thing that's necessary for game solving is randomization, right? You don't want to just you need to hedge your bets. You can't just pick one thing, or else an adversary can exploit you. And that's kind of what I'm using under the hood here to get this more randomized distribution that sort of doesn't lead to this sort of mode collapse behavior that is less than ideal. So in the last, I'm going to skip the proof of this. It's very cute, but you can check the paper if that if you're curious. The TLDR of it is basically that because all of the this game is entirely symmetric, I don't actually need to have two separate players and do adversarial training here. I can essentially do self-play, by which I mean I sample multiple times from my own policy and treat those as samples of two independent copies of the same policy. And because the whole game is symmetric, you can fairly rigorously prove this will still compute a Nash equilibrium of the game. And what this means, like practically speaking, I think, is that you end up with this algorithm we call SP, or self-play preference optimization, that looks very similar to RLHF, but kind of doesn't assume the sort of underlying preference kind of thing. And it looks something like this. So what I'm going to do is I'm going to sample twice my policy, let's say, and I'm going to pass it into a preference model. You can think of this as being some neural network that looks at both psi1 and psi2. So rather than sort of a reward model, right, that looks at a single option at once, right, a preference model is going to look at both of these at the same time. So I'm not assuming I can decompose my preferences into some underlying word function. I'm making no parametric assumption. And you can train this via the same sort of maximum likelihood thing. It just basically, you concatenate the two completions of the prompt into one thing. And then what this preference model will tell you is, okay, you look at its logics and it says, okay, I prefer psi2 to psi1. And what I'm going to do is basically use that as essentially a way to get my reward values. So I tell you I prefer psi2 to psi1, so I'm going to give 2 reward 1 and 1 reward negative. So essentially what I'm doing at a bit here is I'm using the win rate against pi as the reward model. So essentially the way I'm if you want to think of it as a matrix notation, I have some matrix P. And what I'm basically saying is my reward at round T is basically pi times pi at that round. And that's how I'm collapsing this matrix into a single vector. And this gives me a sequence of things, and this this idea, right, of basically taking an inner product between your matrix and your strategy of your opponent. Okay, remind you a lot what we did in game solving, and here, because everything's symmetric, I can use myself as my opponent. So at the end of the day, what this all boils down to is basically the following. You end up with an algorithm that looks extremely similar to the standard RLHF pipeline, with maybe like two key differences. One, rather than fitting a word model that basically is this classifier, I instead fit something that looks at both of these things at once and spits out a score. So this is sort of eliminating the underlying Bradley-Terry, transitivity, reward model assumption. Then when I'm doing policy optimization, I basically sample multiple times. Ask my preference model, which one do you prefer? Use that to complete a win rate. So it says, okay, I prefer side 2 to side 1. Therefore, it has a win rate of 1. So I'll use that for the reward there. And then I use this for whatever downstream RL procedure. So essentially, I'm using just a slightly different way to basically get the reward labels from my downstream RL procedure. And it turns out that this actually matters more than you might think in practice. So I'm going to go through a couple examples of this very quickly. But some friends at Google basically tried this out on, I think this was a summarization task as well. So the numbers here in orange are kind of different instantiations of this algorithm. And what I think is kind of interesting, right, is compared to kind of the vanilla RLHF pipeline, you'll see people prefer things computed by this algorithm like 75% of the time. Same thing over here. You'll see people prefer this, 80, 75% of the time. So all I'm doing here is I'm just fitting a slightly different way of thinking my reference data, and I'm very slightly changing the optimization. And this also holds true if you have access to what I'm going to say is like an online oracle, by which I mean that you can imagine having some fixed preference data set, right? Something someone gave you and you fit this p hat on top of it. Alternatively, what you could do is imagine you have some sort of powerful supervisor model. So think about something like GPT-4, whatever, right? And then rather than sort of taking whatever is in that model, turning it into a word model, and then using that for an RLHF procedure, you can just directly ask that model, kind of as a judge, which of these two things you prefer. And it turns out that actually works pretty well in practice as well. So I think this was again on some sort of summarization task, but I think the cool thing here was that the evaluation here was actually done in like a real human study, and you'll see that like people prefer this sort of thing like 60% of the time to kind of alternatives with sort of the same function class, same models, things like this. And if I remember correctly, I think Stephen had this plot in the first lecture we gave in the course, which kind of points out that using this sort of algorithm, what you can do is you can take a relatively small, let's say 7 million parameter model, and get it to basically get pretty close to like some of these much larger models. Like we're actually beating GPT-4 here, just by being a bit better when we actually use the reference data. So maybe to kind of close off that thing, the points we're trying to make here are basically the following. This Bradley-Terry assumption, maybe you believe that individual people are rational and they have some reward function in their head. They can tell you exactly which completion to a prompt they prefer to other ones. But when you sort of aggregate these preferences, right, especially when you have this sort of partial coverage thing, you can kind of construct these matrices that appear to have intransitivity in them. And then when you try to do policy optimization with this sort of thing, this can lead to this sort of like downstream kind of mode collapse behavior, right? Because there's no reward model in my reward model class that can actually fit the data I saw. So I'm going to basically pick something at random, maybe not exactly at random. I'm going to tie break in some kind of perhaps less than ideal way. And then I'm going to basically say, okay, shift all your probability mass to the peak of this reward model. And this leads to this sort of downstream mode collapse behavior, right? Which is not reflective of the actual diversity of preferences inherent in the population. And the question is what we actually do about this, right? So the solution we just talked about isn't the only solution, but it's one I think is pretty reasonable, is that we don't assume transitivity of preferences. We basically say, all I get is this preference matrix, right? I can construct that without any assumptions. And I back out this criteria that is robust in some sense, that says, okay, give me a policy that's robust against whatever I could compare you to. Of course, right, doing adversarial training in the kind of scale of modern LLMs is really, really hard, right? Like even fitting one copy of the policy in memory is challenging. Fitting multiple is kind of very hard to do. And you have to deal with all the dynamics of adversarial training, which are kind of annoying in practice. So the idea of using a self-play algorithm is, I think, quite nice because at the end of the day, you end up with a procedure that looks extremely similar, the kind of standard RLHF. But all you have to do is basically slightly change what you fit on the preference data and slightly change your optimization procedure. In the sense, you just sample twice. And this gives you a thing where I can essentially eliminate the core assumption we were making in all the stuff we talked about earlier. And this leads to meaningfully better performance across a bunch of different tasks and models, and is being used in a bunch of different systems today. So yeah, I think that's all I wanted to say about this. I think we have maybe like 2 or 3 minutes before folks come in, but any questions about anything?
That's kind of more of a philosophical question,
Okay.
but as the models get better and better, do you think like working with preferences will matter as much because they might be, I guess, maybe more arbitrary? Like I know sometimes when I'm using O1, I don't really care like which one I get because they're both equally strong. Like I still think it's important, like you were showing, to scale up the smaller models. I guess with the larger models, maybe people's preferences will degrade just to like 0.5, 0.5.
That's a good question, right? So ideally what you would do in that situation, right, is you would have an option for your raters that say, okay, I don't actually prefer between these two things, right? The other thing that I think people are doing more and more is they're actually having raters rate things on multiple different axes. So you could imagine they say, okay, maybe in aggregate, I can't really tell you I like this one more, but maybe this one is more concise, and that's kind of nice. But this one actually connects to this other thing I didn't know about, so from a learning perspective, that one's better. And then you can think about, okay, what are the sort of algorithms that kind of use these for multi-dimensional preferences? So I think that like, as soon as you have a model where you basically think everything is good, you can then either say that, okay, I want to just have a feedback collection system so I don't over-optimize, or you can try and get something more nuanced and more complicated and try to answer, okay, can I actually, for example, if I tell you that, okay, what I really care about is conciseness, can I give you a policy that is that?
That makes sense, thank you.
All right. Perfect timing. So I think that is all I wanted to say. These wonderful folks from the Everly Center will now ask you guys a bunch of questions. And yeah, thank you all for your time. It's been a wonderful semester.